Welcome back to the second part of sixth week. We will have the equations of straight lines, planes, and arc length as the remaining subjects. So moving on forward with straight lines. So straight lines are curves, right? And I can represent them in three-dimensional space by giving the coordinates and so on. And what I want here is to represent them in a parametric way that we had already learned for different types of curves. So T is going to be my parameter. A is going to be a point on that line. And B is a vector that represents that line. Either it's on the line, it can be on the line, or it can be outside the line, but in any case, it is parallel to that line. So we could open up the coordinates of each respective element here, like ax, ay, az, bx, by, bz, and then we will have the most general form of our parametric equations. And here I am showing you the sketch of that. I have a position vector A for point P, and then it's the vector that is on the line is represented by B. So let me give you a simple example here, very simple example. I have, let's say, point A. I have point A represented by 3, 2, 0, right? So the straight line in the xy plane through A 3.2, but we can represent that by 3, 2, 0 in the most general case, and having slope 1. So how does it look? A slope 1 looks something like this maybe, okay? And this will be my vector B in this case. And slope 1 I could represent by 1 here, 1 there. So that could be something like 1, 1, 0. And my position vector RT is then gonna be my point on that line, 3, 2, 0, plus T times T is the distance between any point on that line, any generic point on that line. Let me maybe show that to you like this. If my straight line is like that, I have a point P here, and this is my position vector A. This is a known point. So I'm trying to get to, let's say I'm moving in this direction, and this is my generic point, okay? So in the next slides, I will call this one, this original one which I know already, I'm gonna call that P1 actually. And the generic one, which is like X, Y, Z as P. So what I'm interested in is that position vector, and the distance between the 2 points is going to be actually T if the vector is actually a unit vector. The direction that I'm getting on that line is, if it's a unit vector, then T is the distance between any point on that line with respect to my original reference point, and which I'm going to start to call that P1 from the second slide on. So T and my vector on that line is that. So we could write each component as such: 3 plus T and 2 plus T, 0. So at time, let's say 2, where will be my particle? It will be at, for example, 5, 2, 0 coordinates. All right. So the other way we could represent the vector we have here, the line we have here, position vector that I'm interested in, which is my generic case in this case, like any x, y, z, okay? And minus, if I pull this one to this side, that would be my known point, let's say point 1, coordinates of point 1, which will be equal to TB again. And if this is on the line, it's on the line, and it could be outside the line. So our next example will be dealing with such a situation. And note here that, let me draw this better, or write this better. This is my generic point that I'm interested in, and after a certain amount of time, minus my original point that I know on the line. Okay. So let's move on to that example. I have a point, I have a vector that is parallel to my line, which is fine, and then I will try to write down the equation. So for let's say some position vector, I have origin here. This is my first vector, the second vector. So this is the generic point. I'm trying to subtract and take this point's coordinates to the left-hand side and see how it goes. Okay, and the right-hand side will be t times v. V is something I know that is outside the line, but it's parallel to that line. So how do I take this difference? I take from P minus P1. So P minus P1 is represented as P1, P vector, okay? Don't mix those up. So this is exactly equal to P minus P1. And on the left-hand side, I could deal with x generic point minus x1, the point I know, and continue with all the components. And on the right-hand side, I have t. In this case, it's not a unit vector, okay? It's some vector v. So t times that vector, okay? If I rearrange the terms piecewise, so x minus x1 is equal to ta, y minus y1 is tb, and so on. So these are the parametric equations of a straight line. That's how we name it. And if I equate those terms, like the t parameter is common in all of them. So if I leave that alone, I will get the closed form of our equations. So you can see that if the vector that I'm interested, the vector I'm taking the reference, if you will, reference slope somehow for that line. If that's a unit vector, then A, B, C are called the direction cosines that you know from other courses. Okay. If, for example, I have planes and they're intersecting at lines, right? So I could couple these pairs in different fashions. You can read through this to find out the intersection of planes as well. So let's go with a different example. I have point P and I have point Q. I'm interested in this case, the line joining those two points. So I have PQ. I need to first construct, or I can construct first the vector. So this vector can be represented as the difference vector, okay? And I can do that for my 2 points. Let's say I'm interested in PQ vector, so it's Q minus P. Q minus P, you can follow it from here, results in a vector like that. Okay, and what is it equal to, or how can I use this vector PQ? PQ is my vector. I multiply by the T, and then I can define a new generic point M, and I could be looking at the QM vector, which is actually the position vector M minus position vector Q. In that case, I will reach the same construction that I had before, and now I can take the parametric equations of this line and put it in different forms. For example, what do I do here? X is my generic point here, which is represented by the M, minus 1 coming from the X component of Q, and Q doesn't have a Y component, so, and the generic point Z minus 2, that will be equal to, let's say, on the Z component of my vector, minus 5t, and Y component is exactly Y component, and that will be minus t. If I rearrange the terms to leave the t alone, I will get the closed form of that equation. Okay. Let's say I have two lines in the other example. Those two lines, do they intersect? Are they parallel? Are they skewed? That I can decide by equating this to a parameter t1 and the line 2 equation to a parameter t2. Then look at the equations and do the multiplications and rearrange the terms. How do I rearrange them? I have the common term x, common term y, common term z over here. If we equate them, we end up with some equations there. And if we rearrange them again, we will end up with this. So this is what we learned in linear algebra. If these set of equations are consistent, then I will be able to say that they would intersect at some point. If they are not consistent, then they might be parallel or skew. What is skew? You have, let's say, two planes. These lines are residing on those two separate planes, and they have no chance to meet in space. So if you look at this example and solve it by linear algebra, you will see that it's inconsistent, and the points are the lines are skewed actually. Now another example, this is a good one. I have a point, point P right here, 2, 3, minus 1. And I have a line. Line is represented in its closed form, like here, and it's over here. It's passing through a point. And how do I know that, or how do I see that? Okay, I see. Okay, the coordinates, the generic coordinates minus 1. That's my x, plus y. That's my y over here. And z minus 2, why? Because this is going to 2 over here. So that construction I can understand now. So what is the equation of the vector that is on that line or parallel to that line? It will be coming out from here. If you take all these terms to this side, you will see that the vector vt, which is constructed by 2i, 3j, and 1k, which are the coefficients here, can now be used in the parametric form vt, and equation line LL passing through this point will be parallel to this line. So I can see that when I have this vector is also parallel to this one. I could use the same coefficients then on underneath here, like 2, 3, 1, right? And then what is the specific point that I'm interested in, where this line passes through with this slope, if you will? It will be x minus 2, y minus 3, z plus 1, which is represented here. So next up, we have another example, or the same example continues with another question. So we had, I have to find the line that is now perpendicular to the line L. So we need one more step maybe. So I need to write the original line L in a parametric way. I can rearrange the terms for x, y, z components. Then I pick up any random point on that line, and that would have the coordinates x, y, z. X, y, z. Now the vector, I'm just pointing a vector from that P to A, and I can write down the PA vector, which is the difference vector, meaning P minus A vector. P minus A vector means A minus P vector. So it is 2t plus 1 minus 2, it becomes 2t minus 1. So the next term, 3t minus 1 minus 3 will become minus 4 here. T plus 2 minus 1, t plus 3. So this new vector that is on my new line, which is supposed to be perpendicular, is this PA vector. And I know one identity for perpendicular lines. Their their dot products will be 0. And if I dot this PA with my original v vector here, I need to multiply the components piecewise. So like 2 times 2t minus 1, 3 times 3t minus 4, 1 times 3 plus 3, and then equate those. I will come up with a t, an actual t value. That's the distance between this point and that point, probably. This is like a generic solution. Try to approach with the generic point, but in fact it needs to be perpendicular, and I'm talking about a specific distance, so that distance comes out to be related to t. If this was the unit vector, it would be exactly t. In this case, I can rewrite the PA by plugging in the t, so I have the new vector on my line, and I can now use this point and this vector to find out the equation of the LL line, which is now perpendicular to the L line. For planes, we could use similar closed forms. This is just an example here. In this case, I have a constant on the right-hand side, which is not a parameter like t. That's the basic difference you might notice. And how do I sort it out? I give, for example, y equals 0, z equals 0, and x will be 1. And x and z 0, y equals 2, and z is equal to 3. So these are the coefficients where my plane cuts the x, y, z axes. Okay. So now I can do a recollection of the terms in terms of x and y's, I can rewrite the z, and that will be this equation right here. And if I assign the parameter u as x and v as y, you remember that the surface representations from the last lecture, a two-dimensional input space can go to three-dimensional output space in our representations. Like a smooth surface can be curled into something. In this case, it doesn't curl, but just changes its orientations. And now I can parameterize my recollected equation by plugging in the variables instead of x and y, u and v, and rewrite the equation in terms of my position vector RUV. Here we have a vector n and a point P. So we are wondering about the plane that has P1 in it and will be perpendicular to the vector n, which means I'm wondering about the relationship between the plane and its normal. Okay, so the n vector, the normal vector, will be represented by a, b, c components, and then I will define a point that is generic as we did before, p, x, y, z, and we know the coordinates of this point. So p1p vector can be represented by the p minus p1 position vector, which you can see here. And then what is the identity I'm looking after here? If I have a vector on that plane, its multiplication with the plane normal, its dot product with the plane normal should be 0. By using that identity, I can rearrange the terms to get to the closed form of my plane equations. Okay, so if I know the normal vector to the plane, I can use those components here, and these will be coming from the coordinates of my point, which is reflected into the constant here. So let's try to find the distance. For example, we can use these identities in finding the distance between a point and a plane. So how can I approach that? I know the plane equation, let's say, and any point on that plane can be represented by the position or the difference vector AP. AP difference vector means P minus A position vectors, P minus A position vectors, okay? And the normal vector can be given as we defined before. Now, there is some definition over here. It says by definition, but we can make sense of it by taking this n over to the left-hand side. The distance between a point and a plane can be then understood as the unit normal vector, right? If I divide a vector by its length, that becomes a unit vector. So I'm trying to take the dot product with AP. AP is some point over here, random point over here in the plane, and to the actual point that I'm interested in, that's my vector. But what I'm interested in is its projection to the normal vector. Okay, that will give me exactly the d over the distance between the plane and the point. So that I can do and write the AP vector and dot product it with the normal vector and divide by the normal vector's magnitude. So that's how you make a unit vector, and I'm interested in the AP's projection on the unit vector as my actual distance between my point and the plane. So I have two planes here, and they are in closed form. So the coefficients of x, y, z are actually the components of the normal vector, and we can represent it by 2i j minus k here. And the point where these two planes are cutting the y-axis can be found by giving zeros to x and z's, and its y is at -3, y at 5. Then this means that if I try to find any line between these two planes, which I could use to find the perpendicular distance, it could be this on this y segment. And from +5 to -3, I have 8 units. And this could the vector could be pointing either in the positive or the negative direction. It doesn't matter. If you put these on Cartesian coordinate systems, you would be able to see what I'm trying to say here. And if this is the vector that, let's say, pick up the +8j vector, if you dot it with the normal vector, but the unit normal vector, you will be able to get the distance between the two planes. So I suggest that you do this exercise on your own on a piece of paper.